Greetings everyone. My name is Vignesh Singaravelu from PES University. Today, I'll be presenting a paper titled Explainable Germline Variant Pathogenicity Classification with Contextual Insights. This work was carried out by a team of four, including myself. My teammates are M. Govindarajan, Vishnu Srinivas, and Mathew Kurian, and the project was completed under the guidance of Professor Dr. Chaitra N. This work focuses on building an interpretable machine learning system for classifying germline genetic variants as either pathogenic or benign, while also providing contextual information that helps users understand the prediction. I will briefly now talk over the motivation and the problem statement our project is based on. Genetic variants can play an important role in disease development, and accurately identifying whether a variant is pathogenic or benign is therefore an important task in clinical genomics. Many machine learning and deep learning approaches have shown strong predictive performances for this problem. However, most of these systems operate as black boxes, making it difficult for a clinician to understand why a prediction was made. And in high-stakes domains such as healthcare, transparency and trust are often just as important as predictive performance. This was our main problem, the crux of our problem which we are trying to solve. The main problem addressed in this work is the lack of interpretability in existing variant pathogenicity classification systems. I will now briefly go over the overall system data pipeline and explain our methodology. The overall system can be broken down into two main parts. First is the classification model, which is SEN, and second is the contextual assistant, implemented using an SQL agent. To address the problem of limited transparency in traditional machine learning and deep learning models, we leverage a self-explainable neural network, or SEN. Unlike many interpretability techniques that generate explanation after a prediction has been made, SEN incorporates interpretability directly into the model architecture itself. This allows the model to provide explanation alongside its predictions. The second component is the SQL agent. While knowing whether a variant is classified as benign or pathogenic is useful, it does not provide the complete picture. Users often will have follow-up questions such as which diseases are associated with the variant, how frequently it appears in the dataset, or other relevant contextual information. The SQL agent addresses these problems by allowing the user to query it and the underlying database using natural language and retrieve additional insights about the variant. Now I will briefly talk about our data preprocessing steps and the dataset used. The dataset used in this work was obtained from ClinVar's public database. There are two different types of files which can be used from ClinVar: the VCF files and the TSV files. We have taken use of both VCF files for the GRCH38 genomic location and TSV files for context. Here is the exact breakdown of the different files which are used. Variant summary file from the TSV files was our main dataset which contained the different variants and their corresponding features. Genomic location data was also used as a supplementary dataset to our main data. Submission summary, organization summary, conflicting interpretations, gene and allele. These were used as contextual datasets used to populate our SQL agent so that better query and better answers can be provided for queries. Several filtering steps were performed to improve data quality. Briefly going over the filtering steps, out of the dataset obtained from ClinVar, we kept only those with genomic location as GRCH38 and only those variants which are single nucleotide variants, as these are the overwhelming majority. And in SNVs, single nucleotide variants, we kept germline variants, removed invalid and low confidence entries. By low confidence, we mean entries where feature values were missing, either missing or of conflicting values. Map labels to binary classes for classification training, and balance the dataset for undersampling. I will now briefly go over the SEN architecture. The core of our system is the Self-Explainable Neural Network, or shortened down to SEN. The architecture consists of three main modules: the conceptizer, the parameterizer, and the aggregator. Conceptizer converts input features into interpretable concepts. Unlike traditional black box model, it preserves the interpretability rather than transforming inputs into internal numeric representations. The parameterizer generates relevance scores for each concept, indicating how important each feature is for a given prediction. The aggregator combines the concepts and the relevance scores to produce the final classification. The final output would be the classification as well as the explanation, which comes from parameterizer side. For our implementation, significant effort was devoted to data pre-processing. Each feature describing a variant was encoded numerically using either one-hot or multi-hot encoding. As a result, our final model uses an identity conceptizer. An identity conceptizer passes the data as is. This was done just in case in future more work could be done on the conceptizer side. A key advantage of this design is that explanations are generated as part of the prediction process itself, rather than a separate post hoc explanation method. As a result, the model remains inherently interpretable. I will now demonstrate the system in action. This tab is for database query, this is for a single classification, and this is for batch classification. First, let's start with the single classification, where I'll enter the details. After entering the details, I can click on Classify Variant. Classification would start. And then here we have a result with a prediction probability over here, and it's predicted as pathogenic. It first gives us pathogenic supporting features and pathogenic opposing, benign supporting, and benign opposing. Here we can see each feature's name and score. Also, the nomenclature of each feature name takes the umbrella branch name and what they are. So origin, we can locate that over here is de novo. This gives us the entire parent branches classification scores and global features with the highest importance scores. We can also download the relevance file to give us all the features. This only gives us top results, But by clicking on the CSV file, we are now presented with all features, all 34, 33. Now, an additional option in the single classification tab is after classifying, we are given an option to adjust feature weights. When this application would be used by a clinician, say they have some domain knowledge and they want to check out some alternate hypothesis by saying if I give the nonsense molecular consequence less importance compared to the other, how would the classification change? We provide this feature using the UI over here. We are able to adjust feature weights for each feature. Now say for this classification, molecular consequence has nonsense in it, and nonsense is highly contributing towards pathogenic. Say we now lower the importance given via nonsense to now see if the classification would be flipped or if there are any other underlying feature also contributing which is not being shown over here. And there are no benign supporting. So let us see what happens over here. Now, after changing our molecular consequence from nonsense by reducing its weight, we see the prediction is flipped. So we can also verify through weight adjustment about how features are weighing in on the end classification. Now, given this classification, now we can move on to the database query to get more results on this particular variant. Now say I take this allele ID and ask while this is processing, I'll briefly talk over the batch classification. In batch classification, we can upload a CSV file with a lot of variants, and this will classify all of them and provide back another CSV file. This can be used for classifying variants in bulk. Here I have a sample data set. I specified for each variant its origin. Chromosome is not used, but this data is provided in a VCF file with the gene relation, the molecular consequence, and genomic location data. Now I'll provide the same file and process batch. Now I'm given a prediction CSV. When downloaded, I can see for each variant its prediction and confidence scores listed. Now in database query, we have gotten a result, and it talks about different diseases: mitochondrial complex 1 deficiency, Leigh syndrome, Fox-Red related disorder. By querying the database, now a clinician can get more context on what type of diseases this allele, this variant is affecting. This covers the demo of our project. In this table, we have listed our model in comparison with other models and metrics related to them. Deep neural network and other classification models come close to our model in the sense of accuracy, precision, recall, F1 score. and other metrics. Sen, on top of classification, also gives us the contextual, the interpretability, which is absent in black box models like DNN, deep neural networks. In conclusion, in this book, we presented an explainable framework for germline variant pathogenicity classification based on SEN, self-explainable neural network. Experimental results show that the model achieves competitive predictive performance while also maintaining transparency. Future work on this project would include enhancing the current SQL agent to work on a fine-tuned model rather than through prompt engineering, and modifying or tweaking the conceptizer through different approaches. Automated database updates, or rather have a API calling towards a main database for up-to-date information and support for additional variant types. Thank you.